left code demonstration part separate from the presentation part. To begin with, I load some packages, and next as I described in my presentation, I collect data from the website, the PubChem website, since there's no data come along with the original dataset that from the literature. And there are 20 properties I collected from the PubChem website. First three are identities of the chemical, and others are chemical or physical properties. For feature engineering part, I add three features. First two is called number of hydrogen bond acceptor ratio and number of hydrogen bond donor ratio, which are defined by the H acceptor or H donor value by the molar mass. The third feature I developed is the number of oxygen, sulfide, phosphorus, and nitrogen atoms in the molecule, divided by the number of carbon atoms. The log P has a strong linear relationship to the solubility, so this is the most considerable property among all 20 properties. This part I define three error functions, two error function, one R-square function, and I create overall error table that will include these three values for each model, so that we can take a look at the end of this work. Here I go over I made histogram of each feature because all features are numeric, so that we can use histogram to see the distribution of the values in each feature. There are three features that are abnormal because only one value in these three features. They are atom chiral DF, covalent unit, and isotope atom. We will drop them we will drop these three values here. And I also calculate the missing data from the original work. There's no missing data from the original work. And I also calculate the missing value for the data we collected from the PubChem website. Also, there's no missing value. Every chemical has 20 or 23 properties. Therefore, I just randomly drop 5% data as missing data. Next, I define the outliers. So outliers are defined as the absolute z-score larger than 3. Here I define the z-score function. I loop through all the columns and define and find the if the value is larger, if the z-score of that row is larger than 3. And then I drop all of them at once. After drop the outliers, I made a histogram of the data again. For the data distribution adjustment, you can see the molar mass is really left screwed. So by taking the logarithm of this, it could turn the distribution to the normal distribution like you see here. And also I performed the min-max normalization. Actually, min-max normalization is useless for linear regression, for regression problem, but I just did it for lowering the compiling time of the neural network. Here I took a look at the correlation between features to the solubility to our target value. There are several important features: complexity, log P, molar mass, heavy atom, as well as the H acceptor ratio and H donor ratio, which I created earlier. Also, the C other feature I created also has a weak correlation to our target. Here you can see that the output of these two columns are identical, so I just drop one of them. I dropped it here. I also took a look at the collinearity using this pair panel function. For the modeling, as I said in the presentation, I used three methods. The model tree, you can see I trained. First of all, the holdout method for train and test sample dividing is I use 70% for training set and 30% for testing set. Here I train the model tree model and calculate these three values, save it to the overall error table, which we will talk about at the end of this work. Also, I trained the linear regression model. I used back-forward algorithm to delete unnecessary features. Also, I use NNN from RMiner package, which is the fit function here. Mode is set to MLPE. I also test MLP in the next several chunk. Also, I define the number of nodes to 5. Also, I just change several parameters. For example, change the features used for training. I also didn't define the number of nodes using the default value. I also changed the model from LPE to MLP. In addition, I use k-fold cross-validation for training and hyperparameter tuning. Here you can see the model tree with 10-fold MAE actually decreased 0.03 from its hold-up trained model tree. For linear regression, I also use 10-fold cross-validation. The error actually increased. Again, validation also applied for ANN. I tune the hyperparameter by using both holdout method and the k-fold cross-validation method. Let me just jump to the overall performance. This is the hyperparameter using holdout and k-validation comparison. This is the top 5 model that I have. The first one is the artificial neural network with 16 number of nodes. Using MLPE as method among all the features with 10-fold cross-validation. You can see the second place is with default number of nodes, but still use 10-fold cross-validation. Surprisingly, the third place is the model tree with 10-fold cross-validation. This is surprising because model tree doesn't require too much compiling time and too much data process. Also, I tried to make a prediction for dopamine and adrenaline that these two chemicals are out of our data set, which is surprisingly bad. Our model have surprisingly bad performance on these two chemicals. I will show you in this slide. You can see here. I also mentioned in the presentation. The AM bagging has better solubility prediction for dopamine, and with the 16 nodes has better for adrenaline. Thank you.